Question 5 to 8 taken from textbook Self-Practice 2.15. So for this video, I would explain these 4 questions in one go because the way to solve them is the same. Okay, so for these questions, you can see that find the approximate change, find the corresponding small change. Okay, so this one is the 4th application in differentiation, which is to find the small changes. So to find them, we can use this formula: delta y over delta x approximately equal to dy over dx. Okay, so for the small change that we need to find, I will put it here, this delta y part. Okay, and to find this delta y, we need to have 2 things. So one is the dy over dx. Okay, so this one we need to use differentiation to find. Okay, and the other one is this delta x, but I move to the other side first. Okay, so this one will cancel off. Then it would be delta y approximately equal to dy over dx multiply delta x. So to find delta y, we need to have these 2 things. Oh, and also note that this delta x is usually given in the question, right? So for the first question, we have the period of oscillation t of a pendulum and the length of L, and it is given by this equation. So we need to find the approximate change in t where L changes from 9 to 905 cm. So approximate change in t means we need to find delta t. So according to this equation, delta y will become delta t, dy over dx will become dt over L, right? Because L is related to t. So this one will be dl, and this one will be delta L, something like this. So we need to find 2 things. One is this, dt over dl, one is delta L. Okay, so to find the first one, we need to differentiate according to the first the original equation, which is this one. Okay, so let me change this square root to 1 over 2 so we can differentiate easier. Right, so if we differentiate, this would be the answer. Right, so let me explain how I obtain this. So 1 over 2 move to the front, multiply with 2, so it become 1. And eventually we don't write it out lah. Okay, and pi remain it. This whole thing we need to differentiate, and we need to minus 1 from the power, so it becomes negative 1 over 2. Then this is another thing students always forgot, which is to differentiate the things inside the bracket. Okay, inside the bracket. So this one, if we differentiate, this L the power is 1, so if we differentiate, we have only left with the number, which is 1 over 10. So that's why I need to multiply 1 over 10 here. Okay, so once we simplify, we'll get something like this. Okay, and the second value is delta L, which is a small change in L, the length. So this one is given in the question. Okay, so we just find the differences of these 2 values, then we will find the delta L, which is 0.05. And also note that this value is positive because it says L increases, right? Increases. So now we can multiply these 2 values to find delta t. Okay, but this delta t, the answer will be a value. But here we have L, which is an unknown. So how do we solve this? Well, we can use the original value, which is this 9 cm of L, the original value of L. Right? So once we just substitute here, then we'll get the answer, 0.0166 seconds. Right, so you all may be wondering, hey, why use 9? Why not use 905? Because, so usually when we compare stuff, right, we need to compare with something. That something is the original value. Otherwise we don't know, does it change or not, right? So to compare with the original value, then we can see, oh, this thing changes or not changes. So similar concept as here. To find the approximate change in t, what we need to have is a reference or a base or an original value, okay, to find out what is the change in t. Okay, so that's the reason behind lah. Second question, area of a drop of an oil spreads in a circle and increases from 4 pi to 4.01 pi, and we need to find the small change in radius. So this one is delta r. Okay, so for this case, it will be we need to find delta r, and it's approximately equal to dr over dA. Okay, why a? Because this r, which is the radius of a circle, is related to the area, right? So we'll put dA here, and we need to find delta a. Right, so for this one, we need to differentiate from the original equation. But what's the equation? R equals to what? Okay, this we don't know. So usually I would recommend students to compare the value, not the value, the power of R and A. Okay, for R we know that it is cm because it's a length. For A it's cm squared because it's an area. So this one will be has a higher, I would say higher power. Okay, so compare which one has a higher power, then we find the equation from that quantity. So instead of R equals to blah blah blah, let's find A equals to blah blah blah. Okay, much more easier. So if you go back to the question, it says area of a drop of an oil in a circle. So the area, we need to use the circle's area, which is pi r squared. Okay, pi r squared, then we use this equation to help us differentiate and find this thing, the first quantity that we want. Right, so if we differentiate, power move to the front, 2 pi r, and this power I minus 1. Okay, but another thing a lot of students forgot is this one is dA over dr. This one is dr over dA. It's inverted. So what we need to do is to invert this. Okay, so this one originally was 2 pi r over 1, so just invert. It will become 1 over 2 pi r. Right? Then for this delta A, we can use these two values, find the differences, then we'll get the answer. And then to find this delta r, we can multiply these two values together. Okay, this value of r, we need to find the original value, but if you go back to the question, it does not give the original value of r. But this question does give us the original value of a. Okay, and we know this a and r is related to this equation, a equals to pi r squared. So we can use this equation to help us find the original value of r. Okay, and you can refer here. Okay, so as we know, a is equal to pi r squared. Then we substitute the a with the original value, which is 4 pi. Then by rearranging a bit, then you'll get the original value of r, which is 2. Okay, so I just substitute here, then I'll get my answer, 0.0025 cm. So for the third and the fourth question, I will explain in one go. Okay, so for the third question, we have the length of side of the cube is x cm, and we need to find the small change in the volume. So this one is delta V, and it says that the side of the cube is decreasing from 2 to 1.99 cm. Okay, so take note that this one is decreasing. Okay, so this one, to find the small change in the volume, will be delta V approximately equal to dV over x, because the length of the side of a cube is related to the volume, right? So dV over dx, then this one will be delta x. For the fourth question, small change in the volume of the sphere, so this one is also delta V, and it says that the radius decreases from 5 to 4.98. Okay, so to find delta V, almost the same. This one is dV over dr, because the radius and the volume of a sphere is related. Okay, this one is delta r. Right, so let's find the things in red first. Differentiate the original equation. So V would be x cubed, right? Because it's the volume of the cube. X multiply x and multiply x. And this one is the volume of a sphere. So yeah, 4 over 3 pi r cubed. Okay, then we differentiate. So 3 move to the front, power minus 1. 3 move to the front, power minus 1. Alright, so this is the first thing. Second thing, delta x and delta r. So this one, delta x and delta r, we need to to minus the changed value with the original value. Okay, so it's 1.99 minus 2, not the other way around. Otherwise, you wouldn't get a negative number. Okay, so minus, in a way, you get the negative number because here it says decreases. Okay, decreases means this delta will have a negative number. Okay, so once we have these two values, we can multiply them together, but we need to substitute the original value of x and the original value of r first. Okay, so x would be 2 cm, r would be 5 cm. Okay, so once we multiply and we look at the answers.